Somewhere in a quiet room, a screen lit up with a shape that was not supposed to be there. Not a smudge, not a glitch, not a trick of tired eyes after a long night of staring at data. A ring. A vast, deliberate-looking ring of galaxy clusters stretched across a slice of the sky so distant that the light forming it had been traveling toward us since long before. The Earth had oceans, and the moment its true size was measured, a single uncomfortable thought began to spread through the field of cosmology. The kind of thought that does not go away once it arrives. This thing is too big. Not slightly too big. Not a rounding error. Too big in a way that the rules we wrote for the universe say should be flatly impossible. A structure that size should not have had the time to assemble. Not in the entire history of the cosmos. And yet there it was, hanging in the dark, refusing to apologize for existing. That ring was only the beginning. Right beside it, in the same patch of sky, at the same staggering distance, sat a second monster. A long, curved wall of galaxies bending across space like the rim of something we could not see the whole of. Two impossibilities, neighbors, sharing the same cosmic address. And the deeper anyone looked, the worse it got, because they kept finding more of them. Not one anomaly to explain away over coffee, but a pattern. A growing list of giants, each one bigger than the last, each one a quiet act of defiance against the most basic assumption holding our entire picture of reality together. If a story about the edges of the universe is the kind of thing that keeps you awake, do me a small favor and like this video and subscribe. It genuinely means a lot to us and helps more than you'd think. To understand why these discoveries are so disturbing to the people who study the cosmos for a living, you first have to understand the one quiet promise that all of modern astronomy is built on. It is a promise so deep that most people who use it never even say it out loud. It goes like this: the universe, on the largest scales, is fair. Spread your gaze wide enough and every direction looks the same. Pick any enormous region of space, then pick another one billions of light years away, and the two should resemble each other like two handfuls of sand from the same endless beach. No favorite direction, no special corner, no giant lump on one side of the sky and a yawning emptiness on the other. Smooth, even, democratic, cosmologists call this idea the cosmological principle. And it is less a discovery than a foundation, a flat stone slab that every theory, every equation, every simulation has been stacked on top of for centuries. The principle sounds almost too simple to matter, but everything balances on it. When astronomers calculate how fast the universe is expanding, they assume it expands the same way everywhere. When they model how galaxies formed, they assume the starting conditions were the same in every direction. When they draw the grand timeline of the cosmos, from the first searing instant to the cold sprawl of today, they assume no part of space got a head start or a special set of rules. Take that assumption away, and the calculations do not just wobble, they collapse. The expansion rate becomes ambiguous. The age of the universe becomes a question with more than one answer. The neat chain of cause and effect that lets us run the cosmos forward and backward in our minds begins to come apart at the joints. For a long time, the principle looked safe. When astronomers studied the faint afterglow of the early universe, the gentle hiss of ancient light soaked into every part of the sky, it appeared almost perfectly uniform, the same temperature in every direction to a precision that seemed to settle the matter. Yes, the local universe was lumpy. Galaxies clung together in clusters. Clusters strung themselves into long, glowing filaments, and between the filaments yawned vast empty voids where almost nothing lived. But that was the small picture. Zoom out far enough, the thinking went, and the lumps would average into smoothness. the way a rough gravel road looks like a flat gray ribbon from an airplane window. The universe was bumpy up close and serene from a distance. That was the deal. That was the comfort. And then telescopes got better, and the comfort started to crack. The first cracks were easy to dismiss. Astronomers found a structure that seemed a little too large, a chain of galaxies that stretched a bit beyond what felt reasonable, and they told themselves it was a fluke. Search enough sky, and you will eventually stumble onto an arrangement of dots that looks meaningful, even though it is just chance. So they shrugged and moved on. Then someone found another one. Then another. Then a fourth and a fifth and a sixth, each one independently confirmed. Each one measured with different instruments by different people using different methods, and each one pressing against the very same invisible ceiling. There is now a short, dreaded list of confirmed structures that should not be able to exist, and the list keeps getting longer, and every name added to it makes the ceiling look less like a wall and more like a polite suggestion the universe never agreed to follow. The ceiling itself is not a vague feeling. It is a number, and the number comes from real physics. Years ago, a group of researchers sat down and asked a deceptively simple question. Given the age of the universe and the speed at which gravity does its slow, patient work, how large could a single connected structure realistically grow? They ran the mathematics carefully, using the standard model of how the cosmos evolves, the one that has succeeded spectacularly almost everywhere else. They tracked how tiny ripples in the early universe could deepen into clumps, how those clumps could pull in more matter, how that matter could pile into galaxies and clusters and the great cosmic web. And they arrived at a boundary. Anything larger than roughly 1.25 billion light-years across simply did not have enough time to come together. The universe was not old enough. Gravity was not fast enough. That was the limit. That was the edge of the possible. Pause on that distance for a moment, because it is hard to feel. 1.25 billion light-years. Light is the fastest thing there is, a beam that could circle the Earth 7.5 times in a single second, and it would still need more than 1 billion years to cross such a structure from one end to the other. The dinosaurs vanished from the Earth around 66 million years ago. Multiply that span by nearly 20, and you reach the time light would need to travel that maximum allowed distance. By any human measure, it is an absurd, mind-flattening scale. And it is supposed to be the largest anything can be. The grandest cathedral the cosmos is permitted to build. The structures now being found are not nudging that boundary. They are trampling it. Some are twice as large. Some are 3 times. And one, the largest of them all, stretches to something like 8 times the limit. A thing so big that the words we use for size stop carrying any real meaning. These are not edge cases. They are not borderline. They are blatant. And almost every fresh wound to the standard picture has been delivered by a single machine, a telescope that took decades to build, billions to fund, and a flawless launch on a column of fire to send 1 million miles from home. It folded out in the cold like a golden flower, 18 mirror segments locking into a single eye wider than any humanity had ever flown beyond the atmosphere. It was designed to look back in time, to catch light so ancient and so stretched that it had slid out of visible color into infrared whispers. It can see galaxies as they were within a few 100 million years of the universe's beginning, infants caught in the act of forming. And what it has sent home, image after image, spectrum after spectrum, has made the comfortable old model harder and harder to defend. The people who run our most trusted cosmological framework are not standing at podiums announcing its death. They are too careful for that. but they are writing papers with words in the titles like tension and strain and crisis. They are asking, quietly and then less quietly, whether the thing they built their careers on is broken. It is worth understanding what kind of machine delivered all this trouble, because the telescope itself is part of the wonder. It does not sit in low orbit where it could be reached and repaired. It rides 1,000,000 miles out, 4 times farther than the moon, parked at a quiet gravitational balance point, where the pull of the Earth and the Sun conspire to hold it nearly still relative to us. It travels behind a sunshield the size of a tennis court, a layered shroud that drops the temperature on its working side to hundreds of degrees below freezing. Because to see the faint heat of the first galaxies, the instrument itself must be colder than almost anything in nature. Warmth is glare to an infrared eye, so it hides in perpetual shadow, chilled to a stillness that lets it register the dimmest whispers of ancient light, photons that have been traveling for more than 13 billion years before falling at last onto a mirror coated in a microscopically thin skin of gold. And here is the strange truth at the center of all astronomy, the fact that makes a telescope a kind of time machine. Light is fast, but it is not infinitely fast. It takes time to cross space, and across cosmic distances that time becomes enormous. When you look at the sun, you see it as it was about 8 minutes ago. When you look at the nearest bright star beyond it, you see light that left more than 4 years ago. And when this telescope captures a galaxy at the edge of the observable universe, it is reading light that departed when the cosmos was young, light that has outlived the very stars that emitted it. To look far is to look backward. Every image it sends home is a photograph of the past, and the deepest images are photographs of a past so remote that the universe in them is a stranger, hotter and denser and more chaotic than the calm sky we know. The telescope does not show us the universe as it is. It shows us the universe as it was, layer upon layer, like the rings of a tree read from the outside in. And in those deepest layers, where the standard story promised us simplicity and infancy, it keeps finding maturity and excess and shapes that have no right to be there. To really feel why the size limit matters, picture the universe in its first moments, almost unimaginably smooth. The matter that would one day become every star and planet and living thing was spread out with extraordinary evenness. The differences from place to place smaller than 1 part in 100,000. A surface flatter than any mirror ever ground by human hands. But not perfectly flat. There were faint ripples, gentle excesses of density here, slight deficits there, the seeds of everything. And gravity, ever patient, went to work on those seeds. Where there was a little more matter, gravity pulled in a little more, and then a little more, and the dense spots grew denser while the empty spots emptied out. Over millions of years and then billions, those whispers of difference deepened into the towering architecture we see today. The galaxies and clusters and shining filaments draped across the void. But here is the crucial thing, the thing that turns the whole story tense. Gravity is not instant. Its influence travels at the speed of light, no faster. The same cosmic speed limit that binds everything else. So a region of space can only feel the pull of matter close enough that gravity has had time to reach across the gap since the universe began. There is a maximum reach, a horizon beyond which no part of a structure can have communicated with another part, beyond which they could not have worked together to assemble into a single coherent thing. That horizon, combined with the universe's age at any given moment, sets the ceiling. It is not an arbitrary rule handed down by committee. It falls straight out of the most basic physics we have, the speed of light and the patience of gravity. Now consider where these impossible structures actually sit. The largest of the rings and arcs lie around 9 billion light-years away from us, which means the light we are reading left them about 9 billion years ago. We are not seeing them as they are now. We are seeing them as they were when the universe was barely 6 billion years old, less than half its present age. So the question sharpens to a blade. In only 6 billion years, with gravity crawling along at the speed of light, how large could a single structure possibly have grown? The answer the Standard Model gives is that ceiling, that 1.25 billion light-years. And these things are 3 times that, sitting calmly in the data, daring anyone to explain them. It helps to understand what the universe is actually shaped like at the largest scales, because the picture is more beautiful and more bizarre than most people imagine. Matter is not scattered evenly through space like dust in a sunbeam. Over billions of years, gravity has gathered it into an intricate lattice, a structure astronomers call the cosmic web, and it looks uncannily like a network of threads spun across the dark. Galaxies gather at the bright nodes where the threads cross, packed into clusters of thousands. From those nodes run long, luminous filaments, rivers of galaxies and gas stretching for hundreds of millions of light-years, connecting cluster to cluster. And between the filaments lie the voids, immense bubbles of near emptiness, regions so barren that a galaxy can drift alone in the silence for tens of millions of light-years before reaching a neighbor. The voids are not small footnotes. They make up most of the volume of the universe. If you could shrink the cosmos to the size of a city, the bright populated districts would be the filaments and clusters, and the vast majority of the map would be empty, dark countryside where almost nothing lives. This web is what the Standard Model is so good at reproducing. Feed the early conditions into a powerful enough computer, and the simulated universe grows its own web, its own filaments and voids and clusters, in patterns that match the real sky with eerie fidelity on medium scales. That is precisely why the giant arcs and rings are so alarming. They are not part of the web's ordinary vocabulary. The web makes filaments and walls, yes, but not coherent curved arcs 3 billion light-years long, not corkscrew rings, not single connected things spanning a sizable fraction of the observable universe. These giants are written in a grammar the web is not supposed to know. They are sentences in a language the model never taught itself to speak. The most dramatic violation of all was not found by a famous professor with a wall of awards. It was found by a young researcher still finishing her doctorate, working with a method that no large survey had really leaned on before. She was not hunting for a revolution. She was simply following her data wherever it led, and it led somewhere that made an entire field stop and stare. Her name is Alexia Lopez, and her technique was the clever part. Most astronomers map enormous structures by counting visible galaxies, charting where they bunch and where they thin, like sketching a coastline from the lights of seaside towns. She did something different. She used the brightest objects in the known universe as lamps held up behind the dark. Those objects are quasars, the blazing cores of distant galaxies, where a supermassive black hole is feeding so violently that it outshines the hundreds of billions of stars around it, a single point pouring out more light than an entire galaxy. Quasars are so luminous that we can see them across almost the whole observable cosmos, ancient beacons burning at the far edge of sight. When the light from one of those beacons travels toward us, it must pass through everything that lies in between. And whenever it crosses a cloud of gas, a filament of matter, a hidden structure draped across its path, that intervening material drinks a little of the light, leaving a faint chemical fingerprint pressed into the beam. A particular form of ionized magnesium etches a distinctive signature into the quasar's spectrum, a tiny shadow that betrays the presence of gas the eye could never see directly. Lopez collected those fingerprints, thousands of them, and used them to map where the unseen matter pooled and gathered in the deep distance. She was, in effect, reading the silhouette of the invisible against the glow of the brightest lamps in creation. And in her maps, a shape rose out of the noise that she could not explain. A long, sweeping arc, curved like the upper edge of an enormous wheel, traced out by clusters of galaxies and the gas threading between them. On the sky, it spanned about 10 degrees, an arc so wide that if it shone in visible light, it would stretch across a strip of night equal to 20 full moons laid side by side. But it does not glow for our eyes. It sits 9 billion light-years away in the dark, and no human will ever look up and see it. She measured its true length at over 3 billion light-years, nearly 3 times the maximum size the universe is supposed to allow. She named it the Giant Arc, and she carried it to a major astronomy meeting and laid it before her peers. The reaction was not laughter. It was not applause either. It was the wary silence of people who recognize a problem when they see one. Because if the arc was real, it was not a curiosity. It was a contradiction. Some suggested it might be a phantom, a pattern the mind imposes on randomness, the same way we find faces in clouds. There is a genuine danger in this, a statistical trap known as the look elsewhere effect. Search a vast enough field for any interesting shape, and chance alone will eventually hand you one. So Lopez ran the numbers. The probability that the giant arc was a random accident came out at roughly 1 in 100,000. Not impossible to dismiss, but very hard. Hard enough that waving it away required real evidence, not just discomfort. And then she found a second one. In the same region of sky, at the same vast distance, hiding in the same kind of data, a new shape emerged, and this one was even harder to swallow. Not an arc this time, but a ring. A nearly complete circle of galaxy clusters, more than 1 billion light-years across, hanging in the dark like a halo around nothing. Its statistical strength came out even higher than the arcs. And the fact that 2 impossible giants had been pulled from the same patch of sky by the same researcher, using the same method, at the same depth and time, was not something any version of the standard model had ever predicted. The universe had been hiding something out there, and she had caught it twice. There is something worth sitting with in how these discoveries are actually made, because the popular image of astronomy is a lie of glamour. No one looks through an eyepiece and gasps at a ring of galaxies. The work is slow, granular, and often lonely. It is night after night of staring at columns of numbers, at faint dips in spectra, at maps that look like static until, very gradually, a pattern begins to resolve from the noise. And the first reaction to seeing a pattern is never excitement. It is suspicion. A trained scientist who finds something astonishing does not celebrate. She tries to destroy it. She assumes she has made a mistake, that her code has a bug, that her data is contaminated, that her eyes are inventing order where there is only chance. She attacks her own discovery from every angle she can think of, because she knows that the history of science is littered with thrilling signals that evaporated under scrutiny. Only when a finding survives every assault she can mount does she allow herself to believe it might be real. That is what makes the giant structures so heavy. They were not embraced. They were doubted, tested, hunted, and they refused to die. They survived the very people most motivated to prove them false. And consider the audacity of the method itself. To map the invisible scaffolding of the universe, you borrow the light of the brightest objects that exist, lamps burning at the far edge of creation, and you read the faint shadows that unseen matter casts across their beams. You are, in effect, mapping the dark by the light it steals. Every fingerprint of absorbed light is a clue to a cloud of gas you will never see directly. Gas that may itself trace the presence of galaxies and clusters strung along a hidden structure. To assemble a single map this way requires the light of countless quasars, each one a black hole feeding violently across billions of light years. Each one a coincidence of geometry that happened to place it behind exactly the right patch of dark. The wonder is not only that the giant structures exist, it is that anyone found a way to see them at all. Try, for a moment, to hold the scale of the giant arc in your mind, knowing the attempt will fail, because it must. Picture the largest thing you have ever personally witnessed: a mountain range filling a windshield, a storm seen from above through an airplane window, its anvil of clouds spreading for hundreds of miles. The curve of the ocean horizon. Now begin to climb past those things, past the width of a country, past a continent, past the whole round Earth, past the sun and the cold outer planets, past the gulf to the nearest star, which alone would take light more than 4 years to cross. Keep climbing for 3 billion years of light travel. That is the arc. Not a smear of light, but a genuine structure, a curved chain of galaxy clusters bound together by filaments of gas and matter, each cluster itself a swarm of thousands of galaxies. Each galaxy, a furnace of hundreds of billions of stars, a curve built from worlds, sweeping across a third of the way to the size limit's threefold violation. The shape alone is a riddle. Arcs and curves appear in physics for reasons. Sometimes mass bends the light passing near it, stretching a background object into a glowing streak, a trick of geometry we understand well. But the giant arc is no illusion of bent light. It is a real assembly of real matter, curved across a stretch of space so immense that the usual explanations for why things curve fall silent. And the second riddle is deeper still. What holds it together? A structure this large should not be able to be a single coherent thing under the standard rules, because gravity simply could not have reached from one end to the other in the time available to stitch it into unity. So either gravity behaved differently long ago than our models insist, or some process we have not named built the arc, or our entire account of how cosmic structure grows is missing a piece. None of those answers is comfortable. Each one cracks a different load-bearing wall. When Lopez announced the arc, she chose her words with care. She did not stand up and declare that cosmology was overthrown. She said the structure required an explanation. In the careful dialect of science, that sentence is a quiet alarm. It means our best models have nothing to say about this. It means the map has a blank spot where there should be certainty. And the strange part, the part that should unsettle anyone paying attention, is that the arc turned out to be the smaller of her two discoveries. The ring was larger. The ring made even less sense. 2 years after the arc, she stood again before a room of astronomers and unveiled the second giant. She called it the Big Ring, a name that sells it short. A ring of galaxy clusters more than 1 billion light-years in diameter, with a circumference so vast that the entire giant arc, all 3 billion light-years of it, could be tucked inside the ring's outer edge with room to spare. And the ring sat at the very same distance as the arc, in the very same era of cosmic history, only a short angular hop away across the sky. Two impossible things, same neighborhood, same depth, same hand pulling them from the dark. The ring's shape is what makes it worse. A long arc or filament, while shocking at that size, at least belongs to the general family of things the cosmic web is known to build. The universe does spin out walls and threads and bridges of galaxies. The trouble with the arc was only its scale. But a ring is a different animal. Rings in the distribution of galaxies are supposed to come from one specific, well-understood process, a kind of frozen echo of the universe's infancy. In the first hundreds of thousands of years after the beginning, the cosmos was a glowing fog of plasma, and any small overdensity sent a pressure wave rippling outward through that fog. A sound wave spreading in 3 dimensions like the ring of waves from a stone dropped in a pond. When the universe cooled and the fog cleared, those waves froze where they stood, leaving behind faint spherical shells of slightly enhanced matter, each about 1 billion light-years across. Astronomers have measured these shells, used them as cosmic measuring sticks, and they are a triumph of the standard model. But the Big Ring does not fit. It is too large, noticeably larger than the frozen shells should be. And worse, when Lopez examined its full 3-dimensional shape, it was not a shell at all. Seen flat against the sky, it looked like a circle, but traced through depth it twisted, more like a coiled spring, a helix, a corkscrew written in galaxies. Frozen sound waves make spheres. They do not make corkscrews. So the one ready-made explanation in the standard toolbox simply does not apply. That leaves the field in an awkward position, with a confirmed object of confirmed shape and confirmed size, and no accepted story for how it came to be. Lopez herself said plainly that neither of her structures was easy to explain in our current understanding. She did not call them impossible. She called them meaningful. She said they were trying to tell us something. She just could not yet say what. That honesty is the most revealing thing of all. When the person who found a structure admits she cannot explain it, that is not a closed door. It is an open one. And what came through that open door not long after was larger than either thing she had already found. Before going further, it is worth pausing on a fair and stubborn question. How does anyone know the Big Ring is real? How do scientists tell the difference between a genuine cosmic structure and a shape the brain invented by staring too long at a field of random dots? The answer is statistics, cold and unsentimental, and the ring clears the bar. In physics, there is a standard for declaring something real, measured in units that capture how unlikely a result would be by pure chance. One step of that measure means mildly surprising. 3 steps mean roughly a 1 in 1,000 chance of a fluke. 5 steps is the gold standard, the threshold where the odds of random coincidence faking your result drop below 1 in several million. It is the same bar that physicists demanded before they would announce the discovery of a long-sought particle that completes the picture of how matter gets its mass. It is the line the whole field uses to separate signal from noise. The Big Ring crossed that line. Lopez and her colleagues did not rely on a single test. They examined the clustering of galaxies in the survey, checked the pattern with independent methods, and compared the real sky against thousands of simulated random skies. Every approach pointed the same way. They accounted for the look elsewhere trap, the danger of finding meaning in too large a search. They corrected for it, and even after the correction, the structure stood. And the arc, found by a different technique, lent its own weight to the case. 2 anomalies, side by side, both above the threshold of seriousness, both at the same impossible distance. A coincidence can survive one strange finding. It struggles badly under 2. Here is the detail that keeps surfacing whenever these structures are discussed, and it deserves its own moment of dread. Taken alone, each giant is a problem. Taken together, sitting at the same depth in the universe, only a short angular distance apart, they suggest something worse than either one by itself. Astronomers measure cosmic distance and cosmic age with the same single number, the stretch in the light from distant objects caused by the expansion of space. The farther light has traveled, the more space has stretched beneath it, the redder and longer its waves become by the time they reach us. Both the arc and the ring carry almost exactly the same stretch in their light. That means they are not merely near each other on the dome of the sky. They are near each other in depth, in time, occupying the same thin slice of the universe at the same ancient moment. Neighbors in a sky 9 billion light-years deep. What does that mean? Two possibilities, and neither is gentle. Either it is a staggering coincidence, two separate violations of the size limit happening to share the same cosmic doorstep, or they are not separate at all. Perhaps they are two visible features of something single and far larger, two pieces of a giant too vast for any one map to capture whole. Lopez raised exactly this idea. If the arc and the ring are parts of one configuration, then the true object out there is not 3 billion light-years or 4, but something that dwarfs them both, something so large that the process which made it had to operate across a region of space wider than either piece. And the standard model has no such process. Gravity cannot reach that far in that time. Frozen sound waves do not weave arcs and corkscrews together at one address. There is no known mechanism that could plant two giant imprints at the same depth in the same direction, which means either a process we have never identified or a hole in the model deep enough to swallow the whole foundation. She and a colleague followed that thread. They traced a faint curved filament that they had earlier spotted sitting above and around the big ring, and when they followed its full sweep, it reached toward the giant arc, and the two arcs together closed into a circle. A ring so enormous that it encircled the entire big ring within its span, a giant ring drawn on the sky enclosing all the other giants. They named it for exactly what it was, and they tested it the way good scientists must, with two independent methods. One examined whether galaxies clumped along the ring's path more strongly than randomness would allow. The other studied the spatial rhythms of galaxy, clustering across the survey from a different mathematical angle. Both found the structure standing above the threshold of seriousness, strong enough to demand attention. But the most chilling result came from the simulations. Cosmological simulations are among the most ambitious things human beings build with computers. You feed in the conditions of the infant universe, you write in the laws of physics as we understand them, and you let it run forward across billions of simulated years, watching gravity and matter and dark energy braid themselves into a virtual cosmos. These simulations have been triumphs. They reproduce the spread of galaxies on medium scales. They grow realistic filaments and voids and clusters. They predict shapes that telescopes then go out and find. They are, in a sense, the standard model made visible, the best version of our theory that machines can render. The team took one of the largest and most detailed such simulations ever run, a virtual universe modeling a region of space far wider than any real survey, tracking billions upon billions of particles across cosmic time, built to test whether our standard picture can reproduce what we actually see. And they searched it for the giant ring's pattern. They searched and searched. They ran it across every patch the simulation could offer. And the pattern never appeared. Not once. In no version of the simulated universe did the standard physics ever conjure something like the giant ring on the sky. Sit with that, because it is the heart of the whole matter. The ring is not only present in the real sky where the model says it should not be. It is absent from every simulated sky where the model gets its full say. You could run that virtual universe 100 times from slightly different starting points and still never grow anything resembling it. If the standard model were complete and correct, a structure this extreme should at least occasionally appear as a rare statistical outlier. The fact that it never does is the model quietly admitting that it does not contain the ingredient needed to make such a thing. Something is missing from the equations. Something real is out there, and our best theoretical universe cannot give birth to it no matter how many times we ask. So what could the missing ingredient be? Several ideas float through the discussions, none of them confirmed, each of them a doorway into stranger physics. Perhaps the dark energy that drives the universe's expansion is not the steady, unchanging force the standard model assumes, but something that varies, that ebbs and surges across time or across regions of space, sculpting structure in ways our equations never anticipated. Perhaps the very first ripples in the infant universe were not as smooth and random as we believed, but carried some hidden preference, a favored scale or direction baked in at the beginning, from which giants could grow. Or perhaps the answer is something even more exotic, a relic of the universe's earliest instant that we have theorized but never seen. That last idea has a name, and it is one of the more haunting possibilities in physics. Imagine the universe in its very first fractions of a second, hotter and denser than anything that has existed since, with the fundamental forces of nature still fused into one. As it expanded and cooled at an explosive rate, those forces split apart, one after another, in events physicists describe as phase transitions, distantly similar to water turning to ice. And here is the key. When water freezes, it does not freeze as one flawless crystal. Ice forms in many places at once, each patch growing with its own orientation. And where two patches meet that grew in different directions, the crystal cannot line up. A flaw is left along the boundary, a seam frozen into the ice. The early universe may have frozen the same way. As its unified force shattered into the separate forces we know, different regions of space may have crossed the transition at slightly different moments or in slightly different orientations. And where mismatched regions met, a defect could have been sealed into the fabric of space itself. Some of those defects, theory says, would take the form of impossibly thin threads, one-dimensional lines of concentrated energy stretched across the cosmos. Thinner than a proton, far too slender for any instrument to glimpse directly, yet packed with such density that a single short segment would outweigh a mountain range. And a thread of that kind, running across billions of light years, would drag at the matter around it with its gravity, pulling galaxies into alignment along its length over the lifetime of the universe. A thread that curved would gather galaxies into a curve. A thread that coiled would gather them into a coil. An arc-shaped relic would seed an arc of galaxy clusters, and a corkscrew relic would seed a corkscrew ring, which is precisely the strange shape Lopez measured. These threads are not fantasy. They are a genuine prediction of certain serious theories of the early universe, the kind that emerge naturally from the deepest mathematics describing how the cosmos began. We have never caught one. We have never seen an effect that could only be a relic thread and nothing else. But we now have arcs and rings that no ordinary process can produce. And the portrait of what such a thread would leave behind looks unsettlingly like what has been found. That does not make the threads real. It makes them the best motivated guess we have for objects that otherwise have no explanation at all. And here is a humbling thing to hold on to through all of this. Even on its best day, even when the standard model is working flawlessly, it is built almost entirely out of ignorance. Everything you have ever seen, every star and planet and cloud of gas, every atom in your body and in the ground beneath you, all the ordinary matter in the universe adds up to less than 5% of what the cosmos is made of. The rest is invisible. About a quarter is dark matter, a form of mass that emits no light and reflects none, that we cannot touch or see, and whose presence we know only because of the gravity it exerts, holding galaxies together and bending the paths of stars. The remaining majority, the largest share of all, is dark energy, the mysterious push driving the expansion of the universe ever faster. A force we can measure but cannot explain, with no agreed origin and no place in the deeper theories of physics. So when we say the Standard Model describes the universe, we are saying it describes a cosmos that is overwhelmingly made of two things we have named but do not understand. The whole magnificent structure of modern cosmology floats on an ocean of the unknown, and the visible universe is only the thin foam on its surface. That is part of why the giant structures and the early galaxies and the disagreement over expansion land with such force. They are not anomalies in a theory we have fully mastered. They are new cracks in a wall we already knew was made mostly of darkness. If dark energy is not the steady, unchanging force we assumed, if it shifted or varied across the early universe, then the timeline of how structure formed could look entirely different from what we calculated. If dark matter behaves in ways our simulations do not capture, the architecture it builds could be stranger and larger than we predicted. The unseen majority of the universe is the deepest reservoir of mystery in all of science. And every new impossible structure is a reminder that we have been writing the story of the cosmos while unable to read most of its pages. While the structures grew stranger, the telescope turned its golden eye toward the deep past and began breaking the model from another direction entirely. Because the size of things in the cosmos is only one of its sins against the standard timeline, the other is age. The universe, our best theory insists, builds slowly. Stars assemble from cooling gas, small galaxies form first and merge into larger ones over hundreds of millions of years, and only after billions of years do the grand mature galaxies take shape, settling into smooth rotating disks with spiral arms and rich chemistry. Finding a large, fully developed galaxy too early in cosmic history was supposed to be nearly impossible. There simply would not have been enough time. The telescope began finding them almost the moment it opened its eye. Galaxies whose light was so stretched that they had to date from less than 400 million years after the beginning, some from less than 300 million, an eye blink in cosmic terms. And these were not faint scraps, not shapeless clumps of newborn stars. Some were massive, some were bright, some bore the marks of being already grown, with established populations of stars and a chemical richness that takes generation upon generation to brew. The numbers refuse to behave. The Standard Model predicts how many large galaxies should exist at such depths, and the telescope kept finding far more than it should. In some cases, something like 10 times more than the equations allowed. 10 times. Not a small overshoot to be smoothed away with a careful correction, but an order of magnitude, the kind of gap that does not come from rounding. The first instinct, the right instinct, was caution. Were the distances confirmed? Were the masses reliable? Could something about how the telescope sees these galaxies make them appear heavier or more numerous than they truly are? Real work went into this. Some early estimates were revised downward as the analysis matured. A portion of the excess softened under scrutiny, but after all the careful checking, a real strain remained. The galaxies are there. There are more of them than there should be. And they are bigger and more finished than the timeline says they have any right to be. One team described their observations as in serious tension with standard cosmology. Others proposed new physics. The argument is still alive, still unresolved, but the single galaxy that captures the problem most vividly was not even something they went looking for. It appeared by accident, in the background of an image meant for something else. A group of astronomers had aimed the telescope at a distant quasar, one of those brilliant beacons, hoping to study the gas around it. They pointed, they gathered light, and in the field of view, behind their intended target, something appeared that had nothing to do with their plan. A spiral galaxy. Enormous, clearly structured, clearly massive, an unmistakable disk system with sweeping arms, the kind of grand pinwheel that is supposed to take ages to form. They paused, they measured, they worked out how far away and how old it was, and the answer placed it at nearly 12 billion light-years distant, which means they were seeing it as it had been only about 2 billion years after the universe began. Far too early for such a thing to exist. They named it the Big Wheel, and when they published it, they described a giant disk galaxy, several times more massive than our own Milky Way, sitting in an era when no galaxy remotely that large should have finished assembling. Its discoverers did not hide their unease. One of them remarked that, by the ordinary rules, it should have taken the entire age of the universe for a galaxy to grow so large, and yet here it was, fully grown, when the cosmos was still young. It even wore the features of maturity, the defined spiral arms, the flat broad disk, the settled symmetry. Young galaxies, especially at such early times, are usually ragged and clumpy and lopsided, still finding their shape. The Big Wheel had the poise of something that had been spinning gracefully for billions of years, except those billions of years had not yet passed. And then there is how it moves, which is even harder to explain than how it looks. When astronomers study a galaxy, one of the most telling measurements is how fast different parts of it rotate. In a simple system, you would expect the inner regions to whirl quickly and the outer regions to lag behind, the way the inner planets of our solar system race around the sun while the distant ones crawl. The closer to the central mass, the faster the orbit. That is plain gravity. But galaxies refuse to obey. Their outer stars do not lag. They sweep around almost as fast as the inner ones, holding their speed far from the center, producing what astronomers call a flat rotation curve. This stubborn flatness was one of the first great clues that galaxies are wrapped in vast halos of unseen matter, invisible shrouds of mass that grip the outer stars and keep them moving. A flat rotation curve is a signature of a mature galaxy, one that has built up its full halo over an immense span of time. The Big Wheel has a flat rotation curve. At only 2 billion years of cosmic age, that should not be possible. Assembling a complete halo of unseen matter takes time, slow accumulation across the ages, and at that early epoch, the halo should still be gathering, still incomplete, far from the smooth extended distribution that produces such elegant flatness. The researchers compared the Big Wheel's spin and brightness against a well-established relationship that links how fast a galaxy rotates to how luminous it is. A relationship calibrated on nearby galaxies that have had the entire history of the universe to mature. The Big Wheel fell right onto that relationship. It spins like a grown galaxy. It shines like a grown galaxy. It carries the mass of a grown galaxy. And it did all this when the universe was a small fraction of its current age. The paper called it a true outlier, extreme even among the other large early galaxies. Something had reached full maturity in a sliver of the time the standard model allots for the journey, and no one can yet say how. To feel the weight of it, think about our own Milky Way. It holds somewhere between 1 and several hundred billion stars. Its disk spans about 100,000 light-years. At its heart sits a black hole millions of times the mass of the Sun, and it took roughly 13 billion years to become what it is. The big wheel is several times more massive, several times as many stars, a halo scaled to match, and it built all of that in around 2 billion years, a small fraction of the time the Milky Way needed. If the Milky Way's growth were a 13-year childhood, the big wheel reached several times that size in under 2. The standard model has no engine that runs that fast. It grows galaxies through patient mergers and the slow cooling and collapse of gas into stars, each stage measured in hundreds of millions of years. To build something so large so quickly would demand either the most perfectly choreographed sequence of mergers ever imagined, or a fundamental rewrite of how fast gas can become stars in the young universe. Some researchers argue that early star formation simply ran hotter and faster, that the dense gas-rich conditions of the early cosmos let stars ignite far more efficiently than anything we see today. That is physically reasonable, and the most extreme young galaxies do form stars at furious rates. But even pushed to its limits, that idea strains to explain the big wheel's mass at its age. And it was found by chance, in the background of an unrelated image, which raises a quietly terrifying question. If a giant like this can wander unbidden into a single random field, how many more are sitting out there in the vast majority of sky no one has yet examined? If the big wheel is a problem of size and age, the early black holes are a problem of impossible speed. And they may be the strangest puzzle of all. When the telescope began surveying the deep universe, it found something the previous generation of instruments had been blind to: a population of small, intensely red points of light scattered through the early cosmos. At first, no one was sure what they were. But as their spectra were teased apart, a picture emerged that no one had ordered. Many of them appear to be supermassive black holes, monsters millions or even billions of times the mass of the Sun, already grown to enormous size when the universe was only a few 100 million years old. And that should not be possible. Black holes grow by feeding, by swallowing gas and merging with one another, and there is a natural speed limit on how fast they can do it, because the radiation pouring off the matter falling in pushes back against the inflow, choking the feast. A black hole that gorges too quickly blows away its own food. By the ordinary rules, building a black hole millions of times the Sun's mass should take a long, patient accumulation across a vast stretch of time. Yet the telescope keeps finding them fully formed at the cosmic dawn, as though they skipped the slow growth entirely and arrived already enormous. Where did they come from? One idea is that they did not begin as stars at all. Perhaps in the early universe, under conditions that no longer exist, vast clouds of pristine gas collapsed directly into black holes, thousands of times the Sun's mass from the very start. Seeds far larger than any ordinary stellar corpse, giving them a head start that the modern universe could never provide. Another idea is that the densest knots of the early cosmos let black holes feed in bursts far beyond the usual limit, swallowing matter in a frenzy that ordinary physics says should be impossible to sustain. No one knows. What is certain is that the count of these early giants does not match the standard timeline, and that the mystery of how they grew so fast joins the same growing list. Another instance of the early universe doing too much, too soon, too efficiently, in defiance of the patient, slow-building story the model tells. Some of these little red lights may be among the first quasars, the same blazing beacons whose distant cousins would one day be used to map the giant structures, which is a strange and pleasing symmetry. The early universe's most extreme objects becoming the very tools we use to expose its secrets. If the big wheel is a problem of size and age, another discovery is a problem of chemistry, and it lies even deeper in time. The telescope confirmed a galaxy whose light dates from a mere 280 million years after the universe began, an instant after the cosmic dawn, when the first stars had only just begun to burn and the first galaxies were barely condensing out of clouds of primordial gas. The universe then was dark and chaotic, lit only by scattered points of newborn starlight drowning in an endless sea of hydrogen and helium. And yet a galaxy already existed there. Not a formless proto-clump, but a real galaxy with measurable chemistry, bright enough for the telescope to catch its light across more than 13 billion years, and detailed enough in its spectrum to reveal what its stars were made of. That spectrum carried a shock. It showed nitrogen, and not a trace of it but a surprising abundance, far more than such an early galaxy should hold. Nitrogen is not a leftover from the universe's birth. The beginning forged only the lightest elements, hydrogen and helium and a faint dusting of lithium. Everything heavier, the carbon in living cells, the oxygen we breathe, the nitrogen in every strand of life, had to be cooked inside stars and scattered into space when those stars died. That process takes time. Even the most massive stars, which live fast and die young, need millions of years to run their course, and building up a real abundance of nitrogen across a whole galaxy demands multiple generations of stars forming, dying, and seeding the next generation from their ashes. To show the nitrogen enrichment this galaxy displays, in only 280 million years, the cycle of stellar birth and death would have had to spin faster than the standard model expects for that dawn era. It is not an isolated oddity. It belongs to a pattern the telescope keeps returning to from every direction. The early universe appears more chemically evolved, more structurally finished, and more furiously active in forming stars than the orderly old timeline predicts. One leading idea points to a fabled first generation of stars, born from the pure, unsullied gas of the primordial cosmos, perhaps hundreds of times the mass of the sun, burning with savage intensity, living briefly and dying in titanic explosions that flung heavy elements into space far faster than ordinary stars ever could. If that first generation was more massive and more numerous than current models assume, it could have driven a rapid early chemistry, racing the universe toward complexity in its first few 100 million years. Those first stars are a mainstream prediction. Their existence is expected, but their exact nature is unknown because none has ever been directly seen. They would have died long before any instrument existed to witness them, and we can only read their handwriting in the chemistry of what came after. This ancient galaxy's nitrogen may be one of the strongest hints yet that the first stars ran hotter and richer than we calculated, that the opening chapter of cosmic chemistry was written at a speed no one anticipated. There is a quiet wonder folded into this too. When astronomers compared that distant galaxy's chemical fingerprint to certain ancient stars still surviving in our own Milky Way, the oldest and most metal-starved stars, the ones that formed early and never accumulated many heavy elements, they found a resemblance. Those nearby relics, fossils from our galaxy's own youth, carry nitrogen patterns echoing the distant galaxy seen billions of years in the past. It is as if the same rushed early chemistry left its mark everywhere, scattering signatures across the whole cosmos, including in stars that still drift through our own corner of it tonight. The deep past and the local present, written in the same ink. To understand why a galaxy at the cosmic dawn matters so much, it helps to picture the era it came from, one of the strangest chapters in the universe's whole biography. After the first light of the beginning faded, the cosmos entered a long darkness. For hundreds of millions of years there were no stars, no galaxies, no points of light anywhere. Only a vast expanse of cooling hydrogen and helium gas drifting in blackness, growing slowly clumpier under gravity's pull. Astronomers call this the cosmic dark age, and it was exactly that, an age without a single star. Then, somewhere in that darkness, the first clouds collapsed densely enough to ignite, and the first stars switched on, blazing fierce and blue and brief, scattering their light into a universe that had never known starlight. Those first beacons did more than shine. Their fierce radiation began to tear apart the neutral gas around them, stripping electrons from atoms, slowly clearing the fog that had filled all of space, until the universe became transparent and the light of galaxies could finally travel freely across the dark. This great clearing, this transition from a foggy cosmos to a clear one, was one of the pivotal events in the history of everything, and the telescope is now peering directly into its heart. The galaxies it finds there are not supposed to be so bright, so massive, so chemically rich. They are supposed to be faint, ragged, primitive, the first stumbling experiments of a universe just learning how to make stars. Instead, again and again, the telescope finds galaxies that look like they have been running for far longer than the clock allows. Galaxies already glowing with the light of countless stars, already salted with elements that take generations to forge. It is as if the cosmic dawn was not a slow gray sunrise, but a sudden blaze, as if the universe lit its first fires faster and hotter and more abundantly than anyone dreamed. And every one of these discoveries deepens the same suspicion that has been building from every other direction, that the early universe was not the simple, sluggish infant the model describes, but something far more vigorous, far more precocious, far more strange. Then came the map. A team released something that had never existed before, a chart of the universe spanning nearly all of cosmic time, drawn from the telescope's data, covering a patch of sky barely larger than a thumbnail held at arm's length. And in that thumbnail of darkness, nearly 800,000 galaxies. The survey poured hundreds of hours of the telescope's precious observing time into pushing a long-studied patch of sky to its deepest and most complete form yet. The people who led it described being surprised even after years of preparing themselves not to be. The surprise was the sheer number of bright galaxies at the greatest distances, near the very edge of what the telescope can reach. They found roughly 10 times more luminous early galaxies than the models had predicted before launch. 10 times. The theory was not off by a hair. It was off by an order of magnitude. The map revealed something else as well. Supermassive black holes that the previous generation of telescopes had been entirely blind to. Hidden engines at the centers of early galaxies, already feeding and swelling at distances and ages where the standard model does not expect them to be so common or so large. Every extra galaxy, every unexpected black hole, adds its small weight to the same growing conclusion. The early universe assembled its grand architecture faster and more efficiently than our model allows. The discrepancy is not lodged in one object or one narrow slice of time. It runs across the whole depth of the survey, from the relatively recent past all the way back to within a few 100 million years of the beginning. Some argue the excess reflects unusual star formation or quirks of calibration rather than a true failure of the model. That debate is alive. But the raw fact, 10 times too many bright early galaxies, is not a gentle nudge to a parameter. It is a statement that something in our theory is badly underestimating how quickly the cosmos built itself. A fair skeptic might pause here and ask how anyone can possibly trust these measurements at all. How do we know a galaxy is 13 billion years away and not simply faint and nearby? How do we know we are reading the true distances and not fooling ourselves across gulfs no instrument can cross? The answer is a chain of careful techniques, each one checked against the others. The most reliable is to split a galaxy's light into its full spectrum, a rainbow ruled with dark and bright lines where specific elements absorb and emit at precise wavelengths, fingerprints as distinctive as any in a crime lab. The expansion of the universe stretches that light as it travels, shifting every line toward the red end of the spectrum by an amount that grows with distance. Measure how far the fingerprints have slid, and you measure how far the light has come and how long ago it set out. This is the gold standard, and the most extreme early galaxies have been confirmed this way, their distances pinned down beyond reasonable doubt. There is another tool, and it is one of the most elegant in all of astronomy, a gift hidden in the structure of space itself. When a great mass, a massive galaxy, or an entire cluster sits between us and something more distant, its gravity bends the space around it, and light passing nearby is deflected and focused exactly as a glass lens bends light. The universe, in other words, builds its own telescopes out of gravity. A foreground cluster can magnify a faint background galaxy many times over, smearing it into glowing arcs or splitting it into multiple images, letting us glimpse objects that would otherwise be far too dim to detect. Many of the most distant galaxies ever seen were caught only because nature placed a gravitational lens in just the right spot, a cosmic magnifying glass aligned by chance across billions of light years. These lenses are not theories. They are observed constantly, predicted precisely, and they confirm that our understanding of how mass curves space is exquisitely correct, even as the larger picture phrase. So the distances are not guesses. They are measured, cross-checked, and built on physics we trust deeply, which only makes the impossible structures harder to dismiss, because the same tools that reveal them are the tools we rely on for everything else. And while the telescope was counting galaxies across cosmic time, an entirely separate wound in the standard model was festering. One that had been bleeding for years and was finally, formally, called a crisis. It concerns a single number that ought to describe the universe completely and without argument. How fast is it expanding? Ever since the beginning, the cosmos has been growing, every galaxy drifting away from every other as the space between them stretches. The rate of that stretching is captured in one figure, and measuring it seems like it should be straightforward. Find objects at known distances, measure how fast they are receding, and divide. The trouble is that two trustworthy methods of measuring that one number give two different answers, and the gap between them is too wide to blame on simple error. The first method reads the oldest light in the universe, the faint relic glow released when the cosmos cooled enough for atoms to form and light to travel freely, a few 100,000 years after the beginning. The delicate pattern of warmth and coolness frozen into that ancient light encodes a portrait of the infant universe, and fitting the standard model to that portrait yields a precise prediction for the expansion rate. The second method works close to home, building a ladder of distances rung by rung. First, certain pulsing stars whose rhythm betrays their true brightness, allowing their distances to be pinned down. Then, a particular kind of stellar explosion that always reaches nearly the same peak brilliance, usable as a standard candle to gauge distances across enormous stretches of the cosmos. And when these local measurements are turned into an expansion rate, the answer comes out higher than the prediction from the ancient light. Not a little higher. Meaningfully, stubbornly higher. Both chains of measurement have been checked and rechecked by independent teams. Both have survived years of relentless scrutiny, and still they disagree. This is the great tension at the heart of cosmology. Two cameras aimed at the same universe, handing back two different pictures. One is a prediction calculated by running the standard model forward from the dawn of time. The other is a direct reading of the universe as it is today. If both are right, then the cosmos expanded differently in its history than the model says it should have, given how fast it grows now. Something changed between then and now that the equations do not capture. The gap has not narrowed with better data. It has widened. Every more precise measurement on either side has only deepened the disagreement. Recently, a team produced a new local measurement, refining the standard candles and treating every possible source of error with painstaking care. And their result was the highest local value yet, pushing the gap to a level of significance beyond the gold standard. The same five-fold threshold that marks a genuine discovery in physics. The lead scientist described the tension as having turned into a crisis. He said, in plain terms, that the standard model of cosmology might be broken. That is not casual language from a careful researcher. It is a statement that the model's internal consistency has failed at a level demanding a structural answer, not a small patch. And a powerful experiment studying the ancient light independently confirmed its side of the disagreement with even greater precision, while systematically ruling out many of the clever fixes that researchers had hoped might bridge the divide. New forms of dark energy, new particles in the early universe, subtle tweaks to the behavior of the universe's ghostliest particles, all tested as possible bridges, and most of them eliminated. The conclusion was clarifying and uncomfortable. The tension is real, the easy escapes do not work, and whatever causes it sits deep enough in the physics that surface adjustments cannot reach it. And then a striking idea began to circulate, the suggestion that the expansion tension and the oversized structures might not be two separate problems at all, but two faces of a single deeper failure. The argument runs like this. The prediction of the expansion rate from the ancient light assumes the universe is the same in every direction, smooth, and even at the largest scales. If that assumption is false, if the universe actually has a favored direction or varies from region to region, then the prediction is built on a flawed foundation and would naturally come out wrong. And the local measurement, taken in our own cosmic neighborhood, could deviate too. If our patch of the universe happens to expand a little differently from the cosmic average, perhaps because we sit within a large, underdense region that drives a faster local stretch. Both measurements could be honest within their own surroundings and still disagree, if the universe is simply not as uniform as we assumed. In that case, the expansion tension and the giant structures, the arcs and rings and walls, become symptoms of the same illness. The cosmological principle would be wrong not only at the scale of individual giants, but deeply enough to bend the global history of the universe's growth. Two crises, each requiring new physics on its own, might be one crisis wearing two masks. And if that single hidden cause were ever confirmed, the repair to our model would not be a small patch. It would be a foundation poured anew. There is one more line of evidence, and it cuts straight at the principle's most sacred claim, that the universe has no preferred direction. The ancient relic glow, the most exhaustively studied data in all of cosmology, is supposed to look statistically identical no matter where you turn. North, south, east, west, the pattern of warmth and coolness should carry the same character in every direction. But it does not quite. Several stubborn anomalies have surfaced over years of analysis. One half of the sky carries slightly more variation than the other. The largest features in the ancient light, which ought to point in random directions, instead seem to align along an axis that astronomers have wryly nicknamed in the literature. An alignment that should not exist if the universe truly has no favored orientation. Each anomaly alone is debated, picked over for instrumental quirks, considered marginal by some and meaningful by others. But the ancient light is not the only place this whisper of a preferred direction shows up. Multiple independent surveys, mapping entirely different kinds of objects across the sky, have been examined for what astronomers call a cosmic dipole, a systematic difference between one direction and its opposite. More objects or brighter objects on one side of the sky than the other. The surveys cover radio galaxies, infrared selected objects, optical galaxies, distant quasars. They use different wavelengths, different instruments, different methods, built by different teams. There is a known and well-understood dipole that comes from our own motion through space, and it can be carefully subtracted out. But even after removing it, a residual remains in survey after survey, a direction in which the universe simply looks different from its opposite. And those residual directions, drawn from utterly independent data, tend to point roughly the same way. When their evidence is combined, the significance of this preferred direction has climbed past the gold standard threshold. 5 separate chains of measurement, different telescopes, different light, different objects, different teams, all leaning the same way at a confidence level that, in physics, marks a real discovery. If it holds, it is a direct violation of the universe's supposed sameness in all directions. The cosmos would have an axis, an orientation, a quiet preference woven into its largest scales, and that would change the very kind of universe we believe we live in. One survey finding a direction could be a fluke, a calibration error, a quirk of how the data was gathered. 2 surveys finding the same direction is harder to dismiss. But 5, spanning the spectrum from radio waves to infrared to visible light, each built and analyzed independently, all converging on the same axis, is something else. Researchers have hunted hard for mundane explanations. Survey coverage is uneven across the sky. Dust within our own galaxy dims and scatters light, distorting how many distant objects are visible in different directions. Hidden biases can creep into how catalogs are assembled. All of these have been examined, corrected, and accounted for, and the anomaly survives the corrections every time. And the direction it points roughly agrees with the axis seen in the ancient light. The agreement is not perfect, and scientists argue over how closely the various anomalies truly line up. But the clustering of so many independent oddities toward a common direction is statistically difficult to explain without admitting that the universe carries large-scale structure of a kind the standard model does not contain. When the Big Ring first emerged, the most hopeful explanation, the one that would have required no new physics at all, was the frozen sound wave, the relic shell of slightly enhanced matter that the early universe is known to leave behind. That would have been the comfortable answer. But the ring failed that explanation on 2 counts, and both are decisive. First, its size. The frozen shells are about 1 billion light-years across, a well-measured, well-calibrated scale. The Big Ring is significantly larger, a third again as wide, far beyond the wiggle room of measurement uncertainty. Second, its shape. The frozen sound waves produce spheres, which look like rings only because a sphere seen flat resembles a circle. But the Big Ring, traced through its full 3 dimensions, is no sphere. It is that twisted coil, a corkscrew that pressure waves spreading equally in all directions could never make. Lopez and her colleagues addressed the frozen shell idea directly in their work and concluded it cannot account for either the ring's size or its shape. And once that single standard explanation falls, there is nothing left in the conventional toolbox. The field finds itself in a position it almost never occupies, holding a confirmed, statistically solid, physically real object with no accepted account of how it came to be. Building a model of the universe is nothing like designing a bridge. You cannot start fresh and fill in the gaps as you go. A cosmological model must hold together across a staggering range of scales, from the faint quantum tremors in the universe's first instant to the spread of galaxy clusters across billions of light years. And every prediction it makes must match every observation from every instrument. The Standard Model achieved this with breathtaking precision. It predicted the delicate pattern in the ancient light and matched it. It predicted the cosmic recipe of the lightest elements and matched the measured amounts of hydrogen and helium across the universe. It predicted how galaxies cluster on medium scales and matched what the surveys found. It is not a model that failed. It is a model that succeeded enormously and is now showing cracks at the largest scales and at the extremes of cosmic time. Any replacement, or even any serious extension, would have to keep all of those triumphs intact while also explaining everything the current model cannot. It would need to account for the arcs and rings and walls at sizes the present theory forbids. It would need to explain why early massive galaxies are so plentiful and so finished. It would need to make sense of the big wheel's mass and its mature spin when the universe was so young. It would need to resolve the expansion tension, producing one consistent rate that satisfies both the ancient light and the local ladder. It would need to accommodate the preferred direction seen across 5 independent surveys. And it would have to do all of this without shattering the precise predictions the Standard Model already gets right. No proposal yet achieves this. Several partial ideas exist. A dark energy that evolves over time rather than holding perfectly steady might ease the expansion tension. Constants of nature that slowly drift over cosmic history might stretch the available time for early galaxies to form. A cosmology with a built-in direction might explain the dipoles. Each idea solves a piece. None solves the whole, and none has yet run the full gauntlet of observations well enough to win consensus. What the scientists do agree on is that the evidence has grown too strong to wave away. The number of independent anomalies, each confirmed above the standard threshold of seriousness, each pointing toward the same failure of the principle, has crossed the line where coincidence stops being a credible answer. The first great structure to exceed the size limit and seize real attention was the long galactic wall traced through the explosions of dying stars. Then came the giant arc. Then the big ring. Then the giant ring encircling them both. Between and around them sit others, older discoveries that hinted at the same trouble. Vast assemblies of quasars and galaxy walls that once seemed like lonely curiosities. Now there are 7 confirmed structures exceeding the theoretical maximum, found within roughly a decade of one another, identified with different data, different objects, different methods, scattered across different eras and different parts of the sky. That is not the fingerprint of random chance. Random outliers would be lonely and unevenly spread. These are accumulating like raindrops before a storm, and they fall everywhere. What unsettles the careful observer most is not any single structure, but the trajectory, the way the discoveries are speeding up rather than slowing down. Decades ago, the first hints of oversized structure were lonely curiosities, easy to file away as the upper tail of chance, the kind of oddity every large data set throws off now and then. Then the surveys grew deeper and wider, the instruments sharper, and the curiosities multiplied. Each new generation of telescope did not erase the previous anomalies. It added to them. The pattern that should have dissolved under better data instead grew firmer, the way a real coastline grows more detailed the closer you look, while a mirage simply fades. And the structures are not huddled in one corner of the sky or one slice of cosmic time, which is exactly what you would expect if they were artifacts of a single flawed survey or a single biased region. They are spread across different directions, different distances, different eras, found by different teams chasing different objects with different methods. That scattered independence is the most damning feature of all. A coincidence can produce one strange neighborhood. It struggles to produce strange neighborhoods everywhere you look, each discovered by a separate route, each confirmed above the threshold of seriousness, each pressing against the very same forbidden boundary. A senior figure in the field, commenting publicly on one of these discoveries, chose his words with deliberate restraint, calling it food for thought for cosmologists. It was a careful phrase, an invitation to wonder rather than a declaration of collapse. But the restraint itself is telling. When the people who guard the standard model begin describing its violations as food for thought rather than measurement errors, something has shifted in the weather of the science. The structures are no longer being explained away, they are being reckoned with. And the reckoning has only begun. The largest of them all is the one traced by the deaths of giant stars. To grasp it, you have to understand what those deaths are, because they are almost beyond description. When a star many times more massive than the Sun reaches the end of its life, its core collapses in less than a heartbeat. The outer layers crash inward, then rebound, and in certain catastrophic cases, the collapse does not halt at a dense stellar corpse, but plunges further, forming a black hole at the center, and from its poles, two narrow jets of energy blast outward at very nearly the speed of light, drilling through the dying star and erupting into space. For a few seconds, sometimes a few minutes, that burst shines with more raw power than a billion suns, releasing in moments as much energy as the sun will pour out across its entire 10 billion-year existence. These are the brightest explosions in the universe, visible clear across the cosmos, flashes that announce the death of a giant star from the very edge of the observable. Because they are so blinding, these bursts make superb beacons for mapping the deep universe. They flash from wherever the most massive stars are dying, scattered, the standard model insists, evenly across a uniform sky. But they are not even. In one particular region, in the direction of two old constellations, astronomers found a concentration of these bursts far denser than chance should allow. A clustering so pronounced it could not easily be random. Tracing the three-dimensional shape of that clustering, using the distance written into each burst's light, revealed the outline of a colossal wall of galaxies, a structure stretching across a span that beggars belief. By the most recent measurements, drawn from a sample more than doubled in size, the wall may reach across something on the order of 15 billion light-years. Let that figure settle, because it borders on paradox. The universe is under 14 billion years old. Light itself, the swiftest thing there is, has only had time to travel a certain finite distance since the beginning, even accounting for the expansion that has carried distant points ever farther apart. A wall 15 billion light-years long is not a modest outlier at the upper edge of expectation. It is a structure whose very length challenges the bounds of what the observable universe can contain. It is many times larger than the previous record holder, and many times larger than the size limit the principle imposes. If the principle drew its boundary at the length of a single field, this wall stretches across a dozen fields and keeps going. The response to this measurement has been appropriately cautious, and it should be. The mapping relies on those dying star bursts rather than direct galaxy counts, and the relationship between where the bursts appear and where the underlying galaxies truly lie is not perfectly understood. Some researchers question whether the method is reliable enough to confirm a structure on this scale, and the concern is fair. But here is the telling detail. The larger, better sample did not weaken the signal. It strengthened it. The clustering became more defined, not less. And that is precisely backward from how a false signal behaves. Noise fades as you add data, real signals sharpen. When you look harder and the structure grows clearer rather than dissolving, you are looking at something that is actually there. There is a genuine and important distinction the scientists draw between a true structure and a mere statistical clustering. A real structure is physically bound, its parts linked by gravity and shared history, woven into a single thing. A statistical clustering is just a region where objects happen to crowd together more than average, with no single thread of cause connecting them. The cosmic web holds both. Galaxy clusters are real, gravitationally bound. The voids between them are real, carved out by the outward flow of matter. The filaments bridging clusters are real, traceable in simulation and in sky. But at the scale of a wall 10 or 15 billion light-years across, the question of true coherence becomes genuinely hard. Such a wall would contain countless separate clusters and filaments and voids, each a real structure in its own right. And the question is whether the wall binding them is itself one thing, causally linked, or merely an overdense stretch of the cosmic web seen along a fortunate line of sight that makes separate pieces appear to merge into a single giant. Gravitational coherence is the strict test for a structure to be real in the fullest sense, and gravity cannot move faster than light. A wall 15 billion light-years long would require gravity's influence to have crossed 15 billion light-years of space, which the universe has not been old enough to permit. This is the same wall that confronts the arcs and the rings, all of them exceeding the horizon for causal connection. If they are truly single coherent structures, then something other than ordinary gravity assembled them. Those who argue the wall is real point to the three-dimensional coherence of the burst clustering, concentrated in a specific range of depth and a specific patch of sky, rather than smeared randomly through both, which is harder to fake as a projection trick than a flat two-dimensional pattern would be. Critics counter that the detection method carries enough uncertainty that the coherence cannot be proven beyond doubt. The debate matters because it decides how hard a blow the wall lands. A coherent structure that long would be a catastrophic violation of the principle. Even a mere statistical overdensity of that scale is a serious challenge, and the wall is only one of 7. So where does all of this leave us? It is fair to ask, plainly, whether any of it touches the world we actually live in. And the honest answer begins with humility. None of these discoveries changes how the Earth circles the sun, how light moves, how atoms bond, how a falling stone meets the ground. The physics of ordinary life, of engineering and medicine and the machines in our pockets, lives at scales unimaginably smaller than anything a cosmological model describes. A wall the size of the visible universe does not move markets or shift the weather or alter a single moment of a human day. In that practical sense, the principle could shatter entirely, and your morning would look exactly the same. But the implications are not nothing. They simply operate on a different scale, the scale of what we know and what we are able to build upon. Every precise navigation system on Earth leans on physics understood with extraordinary accuracy. Pinning down the expansion of the universe well enough to resolve the great tension would sharpen our grip on the fundamental constants that underpin precision measurement across science. A revised picture of the cosmos might change how we understand the dark energy now accelerating the universe's growth. And the ultimate fate of every galaxy and star is bound up in how that acceleration unfolds. The exquisite techniques the telescope uses to read the light of distant galaxies are cousins of the methods behind modern chemistry, materials science, and medical imaging. And every advance in detectors and signal processing forged for the frontier of astronomy eventually flows back into the technology of daily life. The deepest implication, though, is simpler and harder to weigh. Human beings use their model of the universe as a frame of reference, a quiet backdrop against which we measure our place. The understanding that the cosmos is ancient, vast, and intricately ordered by physical law is woven into the whole edifice of modern science. When that model is revised, the revision reshapes the questions we are even able to ask. It opens doors to new frameworks, new ways of thinking about space and time and matter and cause. A universe that breaks its own supposed sameness at the gold standard level is a universe holding structure we did not know existed and did not predict, which means our map of reality is wrong in a specific, measurable, correctable way. And correcting maps is exactly how science moves forward. Every great revision in our history, every leap from one understanding of gravity to a deeper one, every shift from a familiar physics to a stranger one, felt to the people living through it like the ground giving way. In hindsight, each one widened the world, expanded what humanity could grasp and eventually build. Whatever shape this revision takes, it will be no different. There is one question that hangs over the whole field now, asked aloud in print, attached to one of the most significant chains of discovery in a generation. Not a rhetorical flourish, but a genuine inquiry addressed to an entire discipline. Do we need a new standard model? The researcher who found the giant arc, the big ring, the giant ring encircling them both, who ran the statistics, checked the simulations, and exhausted every conventional explanation, left that question open. Because answering it requires building something that does not yet exist, a model that explains everything the present one gets right plus everything it gets wrong. She is not alone in that uncomfortable territory. The researchers chasing the expansion tension arrived at the same place from a completely different road. The investigators studying the anomalies in the ancient light reached it from yet another. The observers cataloging the impossibly early galaxies came to it from the deepest edge of cosmic time. Different methods, different objects, different regions of sky, different eras, and the same destination. The standard model is under pressure from every angle at once. What makes this moment so rare is the marriage of precision and breadth. Each anomaly is now measured with enough rigor that it cannot be brushed aside as noise. And there are enough of them, independently confirmed, all pointing at the same underlying failure, that the accumulation cannot be explained as a scatter of unrelated accidents. The hope, stated plainly and without drama by the woman who found the giants, is that these ultra-large structures are telling us something important about the universe, that their sizes and shapes and locations must carry meaning. The meaning is not yet clear. That is where the field truly stands, not at a resolution, but at a threshold. The evidence that something is wrong has crossed the bar of scientific confidence. The evidence for what comes next has not yet arrived with equal force. This is how science behaves at its frontier, not with sudden tidy answers, but with the slow gathering of anomalies until their combined weight forces a new framework into being. One understanding of the heavens held until observations demanded a deeper one. A familiar physics reigned until a stranger one became unavoidable. The standard cosmological model worked beautifully until a golden eye 1,000,000 miles from home turned toward the edge of the observable universe and began sending back things that were not supposed to be there. And the eye is still open. The data is still arriving. Every new observation lays another stone on a picture already strange enough to demand rebuilding from the ground up. What that new picture will look like, who will draw it, and what it will reveal about the deepest nature of space and time, no one can yet say. Imagine, for a moment, that you could travel along one of these giants, that you could ride a beam of light from one end of the giant arc to the other. you would set out past the edge of our own galaxy, leaving behind every star you have ever seen named in the night sky, and you would not arrive at the far end of the arc for more than 3 billion years. In that span, suns would be born and die behind you by the billion. Whole galaxies would spin through dozens of slow rotations. The light you rode in on would have left its starting point before complex life ever crawled across the floor of Earth's young oceans, and it would reach the journey's end long after. And for that entire unimaginable voyage, you would still be traveling along a single structure, one connected thing, a curve of clusters and filaments that the universe was supposedly never old enough to build. The scale does not fit inside a human mind. It cannot. We did not evolve to feel distances like these, and the honest response to them is not comprehension, but awe. The particular vertigo that comes from standing at the lip of something genuinely too large to hold. And the deepest unease is not any single giant, but the suspicion that they are connected, that the arc and the ring and the Great Wall and all the others are not separate accidents, but glimpses of a pattern we are only beginning to perceive. Like a person in a dark room running their hands across the surface of something vast, feeling an edge here and a curve there, slowly realizing that all the pieces belong to one enormous form whose full shape they cannot yet make out. That is where cosmology stands tonight. Hands outstretched in the dark, fingertips brushing the contours of a universe far stranger than the one we thought we knew. Beginning to grasp that the map we drew with such confidence may have captured only the smallest, nearest corner of the truth. For now, picture once more that ring on the sky, that impossible circle traced in galaxies, 9 billion years of light away, far too large to exist, and yet existing all the same, patient and silent and utterly indifferent to the rules we wrote for it. Picture the wall that may stretch across the entire reach of the visible universe, mapped by the death cries of giant stars. Picture the great wheel of a galaxy that grew up before it had the time, spinning with the grace of something far older than it could possibly be. Picture the faint chemical signature of a galaxy from the cosmic dawn, already rich with elements that should have taken eons to forge. Picture the 800,000 galaxies crowded into a thumbnail of sky, 10 times more than anyone expected. And then picture the expansion of the cosmos itself, refusing to settle on a single rate, and a preferred direction whispering through survey after survey, an axis the universe was never supposed to have. Each of these alone might be a puzzle to set aside for a quieter year. Together they form something heavier, a chorus of strangeness, all singing the same uneasy note. The box we built to hold the universe is straining at its seams, and the cosmos, as it keeps demonstrating with every new flash of ancient light, has never once agreed to fit inside it. Somewhere out there, larger and stranger than anything yet measured, the next discovery is already on its way, its light crossing the dark toward us, as it has for billions of years, indifferent to whether we are ready. And when it arrives, it will ask the same question all the others have asked, the question that now hangs over an entire science and refuses to be answered. What if everything we thought we knew about the shape of the universe was only the smallest corner of a far vaster and more astonishing truth, still waiting in the deep for someone patient enough to look?